So let's start the afternoon session second. So the first speaker of this session is Konstantinos Sfetsos. And he's going to tell us about lambda deformation. Yes, please, sir.
Okay, thank you. So, I would like to thank the organizers and the center for the invitation to present this talk here. This is the first time in Taiwan, and in fact the first time for me in Paris. So it's a very nice experience. So, the work I'm going to be talking about has to do with something which is called now lambda-deformations. And it has various aspects which have been worked the last 2-3 years or so, starting with this work. And various aspects of the work have been worked out with different collaborators, supergravity embedding, mainly with Daniel Thompson, who is in Brussels, moving now to the University of Swansea in England, in the UK. And also people like George Sfetsos, Konstantinos Sfetsos, where we worked RG flows, normalization group flows for these models, and also in relation to some other kind of deformation which people have constructed in the literature, which are called eta deformations, which I don't think I will have time to talk about. And in addition, with George Georgiou and Sfetsos, anomalous dimensions of operators in these theories. So basically, I could have talked my talk construction, integrability, and exact results with one S of deformed conformal field theories. So to give you a little bit the context and some of the ideas, let me remind you of something that everybody knows in this room. For instance, we have an equal for super Yang-Mills theory, which for large n exhibits integrability, and at the same time is maximally supersymmetric, and also the corresponding dual program is also integral as it has been shown years ago. Now, the idea is to take a theory like this, which is very beautiful, and maybe reduce the amount of supersymmetry, but at the same time retain aspects that make it integrable. One such deformation of the theory, which retains integrability but reduces supersymmetry, it has to do with what is called gamma deformations, which reduce supersymmetry when equal 1, still conformal, and the corresponding gravity dual, which has been worked out more than 10 years ago, is also integrable. However, a word of caution here is that when you reduce supersymmetry, but still retain some amount, you might not retain integrability. For instance, we have an equal 1 theories, in which in the gravity sides there are string solutions which are not integrable, even chaotic. So, out of this transparency, we learn that supersymmetry doesn't always imply integrability.
Sorry, a very naive question related to my ignorance. What does it mean that the gravity dual is integrable?
It means that the classical equations of motion, for instance, can be formulated as a Lax pair.
Ah, okay.
Okay, so I'll give you some example of this later on, in the context of my models. So the kind of models that I would be talking about here is models that break supersymmetry completely but retain integrability. Okay, another motivation for this work has to do with field theories and the quantum behavior of field theories, which is encoded usually in the beta function equations or the anomalous dimensions of operators. These two objects, which are the subject of a lot of interest over the decades in field theory, traditionally are worked out perturbatively, order by order, in some set of small parameters. Now, the question which I'm going to be addressing, I think, successfully, is if I can have models where I can compute the beta function and their numerous dimensions exactly to all orders in perturbation theory. I will show you, together with this, it has also a related question, is if I can compute correlation functions exactly. Now, as I said, these are typically very difficult tasks, and we are very excited as physicists to have examples where this can be done. And I will show you that this is possible, namely that I can compute anomalous dimensions and the beta function of these series exactly. So this is an introduction. Now let me start with the kind of models that I will have in mind. Now the field theories or the models that I will be using are two-dimensional sigma models. So when you see here integration is of course d squared sigma. So it's two-dimensional sigma models, and in particular, the subject of the model I would be interested is this one in the box, which is a conformal field theory, which is supposed to be given by the Wesso-Minor-Witten action for a general group G, semi-simple group G, parameterized with some group element little g. Now this is the conformal field theory, and the action is given by many years ago, by what I wrote here. Now d plus and d minus are derivatives with respect to the light point coordinates of the two-dimensional vortices, so maybe tau plus sigma and tau minus sigma. Now what makes this theory conformal is the fine-tuning between the coefficient of this term and that term here. But of course, I will not be interested in the first term, but what happens to the theory when I perturb it with the second term. The second term, as you see, is a current bilinear, so J plus and J minus are the currents of the theory, which in the absence of this term are currently conserved. So the del minus on J plus and del plus on J minus are 0 when this term is not in here. And I would like to know classical and quantum aspects of that theory. Now, this has been called the non-abelian Thiering model. Non-abelian because the group is non-abelian. And Thiering model because one motivation to construct this perturbation has to do with work many years ago, which had to do with fermions in 1+1 dimensions, which interact with the quartic interaction among themselves. And one can think of the quartic interactions after bosonization of the fermions as a term of that form. Now, as I said, when the perturbation is 0, so it's turned off, so this parameter lambda is 0, then we are at the conformal point, so we have this symmetry, so we have left and right transformations with different group elements, omega plus and omega minus, which are functions of the either sigma plus or sigma minus. These are the currents I was talking before, which one can build explicitly using the group element in some representation matrices TA, which forms some Lie algebra. Now, the word lambda deformation has to do precisely with the letter lambda, nothing more mysterious than this. And now, the extra term, first of all, although these currents are of dimension 1 in the conformal field theory, this bilinear incurrence, because A sums up in the full set of generators of the Lie algebra, is not a marginal perturbation. It would have been a marginal perturbation, in fact exactly marginal, if A was restricted in the Cartan torus of the group, but A here takes values in the entire, its overall generator. So if it's SU2 is A is 1, 2, 3, etc. For SU2 is 1, 2, 3. Okay? Now, this particular term here breaks the symmetry to this global one. So the theory is still invariant under this transformation, but it's no longer conformal. So we expect that this parameter that drives it away from conformality runs with the energy scale. So in one of the objects, which I will show you how to do it, is how to compute the beta function corresponding to this lambda, and how the dimension of the currents J plus and J minus changes from 1 to 1 plus something, which is the anomalous dimension, and how the anomalous dimension depends on this parameter lambda. Okay, now the idea is now once we have an action like this, we can proceed two ways. If I want to do quantum aspects, we can do a field theory computation and let's say perturbatively to a certain order compute the beta function anomalous dimensions up to let's say 2-3 loops in lambda. This is not what I would like to do, because then I would do something that in principle everybody can do, and it's all traditional, doesn't give you the information I want to give you. The idea is to construct the effective action for these models, which takes into account all lambda corrections, and from that, using techniques which have to do with RG flows in two-dimensional sigma models, which have been developed in the past, then compute the beta function. And in fact, I will get much more than this. So the starting point to construct this action is, again, what I have in the box, which is, as before, the Weissman-Witten model for G. This is the same I showed you before, just repeat it here for convenience, plus the second term, which is called principal car models, which also have been introduced in the past, which looks kind of similar, the action is here, looks kind of similar with like this, but without this term. This term is crossed out. Now, again, this G tilde, just to distinguish from G, is in the same group, and kappa squared is just the radius, so some overall scale. Okay, we have K, which is quantized for the Weissman-Witten action, and kappa squared, which is some scale. Now, this theory has this global symmetry. In fact, this theory is integrable. It has been shown that if there is a formulation of the equation of motion, the Lax pair, so there is an infinite number of conserved currents. So, to begin with, the theory we have is integrable because we have an action like this one, which is conformal, which is, of course, integrable, and also an action which is integral. So the sum is integral because these two terms do not talk to each other. Now, this action here has a lot of symmetry, as I was showing you. This one has this global symmetry, so in principle you can gauge some subgroup of this symmetry, and I choose to gauge this particular subgroup where lambda belongs on the group and acts on a vector vectorially on the group element corresponding to the Weissman-Witten, and only from the left as far as the group element entering the principal current model action. So lambda, as I said, is a group element on the group G. Gauging means that I make this transformation local, so lambda is not a constant, but it could depend on sigma plus and sigma minus. And that means I have to introduce gauge fields to do that job. Now, the gauge fields introduced, it's well known, for the Weissman-Witten action, they are introduced in this particular way. If you ask yourself if it's just replacing derivatives by covariant derivatives, it's not the case. Yes?
I think I missed something. So, in the Weissman-Witten model, you also have the principal chiral model.
Yes.
So
go back.
This the first. So
the Weissman-Witten model and this one.
So why you add again? Why you add again the primary chiral model? Why you add this term again?
This one?
Yes.
Okay. This one is one of the two terms of the Weissman-Witten action. Now, the principal chiral model is a model which is similar to that, but without this term. That has huge consequences. For instance, the model is no longer conformal. The conformality of this model relies on the precise relation between the term, the coefficient of this cubic term and the coefficient of the first term.
So basically you are changing the k. You are shifting the k.
No, it's
This is k, this is kappa.
But this is belongs to the same group. GT
Yes, but
belongs to
this
the
is,
same group.
yes, but it's a different group element. It's like having SU2,
I see,
for instance, SU2 here,
I see,
SU2 there.
I
Okay?
see.
So K, for topological reasons, or algebraic in general, is quantized. It has to be a positive integer, 1, 2, 3, etc. But kappa square can be a continuous parameter. Okay? Now this model just this people were interested initially for this model because the running of the beta function is negative, so they resemble QCD, only that aspect of course, and they were thinking that somehow by learning about these models, they can learn something about QCD. I don't know if that's true, but after a while, certain things in physics have their own life on their own, okay? Okay, so as I said, we introduce gauge fields, A plus minus, which take values in the Lie algebra of the group. And in order to make the symmetry from global local, we have to add certain terms in the action. You have to modify the Wessel-Witten action in this particular way, and the action corresponding to the principal Carré model in this way. For this action, you just replace derivatives by covariant derivatives. The comment I made before is that this replacement does not work for the case of the Wessel-Witten model. What works is what I wrote here. Now, having a symmetry which is from global local, that means I have redundant degrees of freedom, so that means I have to gauge fix something. Now, I have many choices, so I have to fix dimension G parameters, because this is the dimensionality of, this is how many parameters are in the group element lambda. And I can choose some of them to be here, some of them to be there. The most convenient choice is to gauge fix G tilde to 1. There are no fixed points in this transformation because the group action is only one-sided from the left. So I choose the most convenient gauge fixing, which is G tilde 1. Say it again? I'm sorry, the G? You mean for this part? Yes. For this part, yes. But the gauge fields still remain in here and in a quadratic term from this action. Let me continue. If you don't solve your question, then we discuss again about that. So once I gauge fix this way, then the action reduces to that. This is the part corresponding to the Wessel-Witten, which is the same, plus this quadratic term in the gauge fields. So if I didn't have this term, this would have been another conformal-free theory corresponding to the coset conformal-free theories. This part here breaks this conformality. Now there is a standard procedure which I'm not going to repeat, which tells you essentially that in a path integral, imagine you have a path integral, if you integrate out the gauge fields A plus A minus, they appear with no derivatives, so it's possible to do it. They appear also quadratically, so it's some Gaussian integration. And then you substitute back the classical, equations of motion, and this is what you get. This is the action which is central in this work. It's an action that depends on two parameters, k, an integer, and lambda, which is the deformation parameter. And it has a term which is the conformal-free theory corresponding to this current algebra, Wessel-Witten model, plus this term here. This term here contains, in a non-trivial way, the deformation parameter, lambda inverse. This is the unit matrix, and this D is defined by what I wrote here. Now this D is it's easy to compute. For instance, it's a rotation matrix. So if you look for SB2 in some classical mechanics book, Goldstein, for instance, you find the expression, if you parameterize G in terms of Euler angles, then this TA are just Pauli matrices. Then you form these trays and you find the 3 by 3 matrix for SU2. And lambda is a parameter which is formed by the original K of the Wilson-Witten model and kappa squared, the radius of the principal chiral model. So it turns out it's more convenient to trade kappa squared, the radius of the principal chiral model, for a new parameter which is this lambda. Okay? Now let's see, there is a generalization of this for general deformation matrix, which is not.
Sorry, this deformation is relevant?
This deformation is relevant, yes. Okay. In fact, it's called marginally relevant because the engineering dimension of the perturbation is still 1,1. But it's not exactly marginal. So we'll see the beta function. We'll see that. Okay, now first property is that for small lambda, this action becomes what I started my talk. Wilson-Witten plus a current bilinear. You see that it's easy. It's just for small lambda, this term dominates over that, and then because we have another inversion, we get the term I was talking about. Now, because we are away from the conformal point, we expect this derivative here, where t is the logarithmic mass scale, to be non-zero. So that means a running of the beta function. K is an integer, so we don't expect it to run under RG flow. In fact, this is correct, it turns out.